Let's talk about the kinematic analysis of a shuttle run. All right, so we're going to do kinematic analysis. And this is continuing to practice understanding our understanding the relationships between position, velocity, and acceleration. So kinematic analysis of a shuttle run. Now, expecting most of you have done a shuttle run in some sport, and that's where you run back and forth in a straight line at different speeds. Sometimes you're sprinting, sometimes you're doing a slower speed or what have you, but it's a shuttle run in that you're going back and forth, back and forth, back and forth, changing directions, and also trying to accelerate and decelerate, speed up and slow down. All right, so let me draw out a laboratory reference frame, sort of describing that shuttle run a little bit more. So we have that horizontal dimension, we have the vertical dimension, this would be the ground, and then we also have a medial lateral direction. All right, and we've got a person who's going to be running. That's my runner. And the person's going to run forward, stop, turn around, and then run back. So forward and then backwards. And they would turn around and run that direction. Or sometimes you run sideways and sometimes you run backwards, whichever way it is. All right, so when we do a kinematic analysis of a movement like this, we set up our laboratory reference frame. It does not move. And then we look at our movement, and then we decide on one dimension to analyze. And then we will take that dimension, whether it's the X, and look at how the X position is changing over time, or the Y position over time, or the Z position over time. And each of these are interesting in their own right. So we may be interested only in the horizontal movement. We may be interested only in the vertical movement of the person moving up and down while running, or we may be interested in any side to side movement that's happening over time. So we pick one dimension and then we dive deeper into that dimension. And then ultimately we put those three dimensions together to try to understand the movement in total. So for us, it makes sense to start off by looking at the horizontal movement because I'm obviously already drawing the description of moving forward and backward. So the eye is really drawn towards this horizontal dimension. And then at that point, we want to look at the relationships between position, velocity, and acceleration in this dimension only. So now we don't concern ourselves with the person moving up and down or even any side to side movement. We're only going to look at where the person is at any moment in time. And then we do our position parameters, and we have two. We have distance, total change in position. My pen is running out of ink. Total change in position. Oh, where's my other good pen? There it is. Total change in position. And our units are units of length. And this is a scalar, meaning it's represented by magnitude only. And we may be interested in the distance. We may be interested in, we're in 10 yards this way, 10 yards back, the total of 20 yards. The other position parameter we use is displacement, straight line distance between 2 points, between final and initial. And we use the equation delta S equals SF final position minus initial position. And units, again, are units of length. And this is a vector, whereas this is a scalar. Distance is a scalar. All right. And remember, anytime we do vector, we have to deal with both magnitude and direction of the parameter. All right, so that's position. Our other kinematic parameter that we look at is velocity. This is the time rate of change of displacement. So we use V equals delta S over delta T, final position minus initial position divided by the change in time. And our units are any units of length over any units of time. So for example, e.g. meters per second, miles per hour, feet per minute, whatever it is, okay? Now remember that this is a vector, has magnitude and direction. And our other parameter that's very closely related to velocity, in fact, if you're in a physics class, an instructor may actually say speed is the magnitude of the velocity vector. And that's fine. But typically in our area, we just provide the equation for speed being distance over time. So if I look at the total change in position, forward and backwards, I would divide that by time and I would have an average speed that's being used. Either way is okay. It's just good to clarify, how you're doing it in terms of who you're talking to and what you're working with. I use speed a lot of times just to capture our understanding of this parameter to really understand velocity, all right? But if I do ask for an equation for speed, I'm looking for distance over time, whereas velocity, we're looking for displacement over time. The same units for speed, and this is where it can get a little confusing, but speed is a scalar, it's magnitude only, whereas velocity is a vector and has magnitude and direction. And what we really want to do is understand the usefulness of velocity as a vector. Okay, and that's where we're really going. We understand the magnitude of rate of change of position because we know speed so well from driving a car or riding a bike or what have you. All right, and then the third kinematic parameter that we use in our kinematic analysis is acceleration. And that's the time rate of change of velocity. So we do A equals delta V over delta T, VF minus VI over the change in time. And the units here are any units of velocity over units of time. So for example, meters per second, or meters per second squared. All right, those are the same piece or same units. Acceleration is also a vector, so it's represented by magnitude and direction. And what's really important, and we'll emphasize that in this presentation, the direction of the acceleration vector does not indicate direction of motion. Okay, so that's a really important point. The direction of acceleration by itself does not tell us the direction of motion. For example, if I always use a projectile as an easy way, easy example. If we have a projectile, so an object in the air, and gravity is the only force acting on the projectile. Gravity causes all objects to accelerate negative 9.8 meters per second squared. If I tell you that there's a projectile and it's accelerating negative 9.8 meters per second squared, you cannot tell me, is that object moving up or is it moving down? Is it slowing down, moving upwards, or speeding up, moving downwards? Because the direction of the acceleration vector by itself does not indicate direction of motion. I need the direction of the velocity vector, or even the direction of the position vector will get me there. Okay, but direction of the velocity vector does tell us direction of motion, as does the direction of the displacement vector tells us the direction of motion as well. Okay, so now we've got our kinematic analysis set up. We are looking into horizontal dimension. So now what we want to do is use our basic understanding of what a shuttle run is and look at the relationships between P, V, and A at this point. All right, so let's do that. So now what I'm going to do is I'm going to draw 3 plots. The first plot will be position versus time. And I'm going to use, I'm going to put in horizontal here. And I'm going to put, I'll put meters as our dimension. Okay, remember this is the X dimension for my global reference frame. All right, so this is now 0, the starting place. And then this mark up here would be over where the person turns around. Okay, so this mark here would be this mark here. So I run across the floor, I run back to the starting place. I run over to the cone that's on the ground, I run back, okay? All right, so that's our displacement or our position, all right? Horizontal position. And then right below that, I'm gonna put another plot, which will be horizontal velocity. And because I used meters here, I'm going to use units of meters per second here. And now I've got a region for positive velocity and regions of negative velocity, and here's 0 velocity, and this is still time on this axis down here. What does the positive velocity mean? It means moving forward. So I'm going to actually put forward here. I'm going to put backward here. The positive velocity simply means I'm moving towards the turnaround point. The negative velocity simply means I'm moving back towards the origin. So this is backwards. All right. Okay, so now I'm going to do one more plot, and that is going to be the acceleration, horizontal acceleration versus time. So I've got time on this axis, and these all line up, and now I'm going to put, horizontal acceleration. And now, because I use meters per second here, I'm going to use meters per second squared for my units here. And again, I've got positive regions of acceleration, I've got a 0, and I've got negative regions of acceleration. And I really want to walk away from this presentation having an understanding of what the positive acceleration means and the negative acceleration. All right, so those are our 3 plots. Now we're going to work on the relationships of these plots. So what do we have here? Well, I'm going to draw it out like this. Here's our starting place, and I'm going to do a midpoint here where we get to the other side of the court, where the cone may be, where we turn around, and then we start running back to the starting place. All right, so this is time 1. This is a time later than that. So I'm further along in the horizontal dimension. And then I run back to the origin, but time keeps moving forward, so I have to put that dot all the way over here. All right, now what I'm going to do is exaggerate some of the change in position that we may have here. And the way I'm going to do it is I'm going to draw a straight line like this. All right, and I'm going to say I'm looking at the change in position in that period of time. I can actually figure out what velocity is by looking at this line. And velocity, we know, is going to be related to the slope of the position versus time plot. Remember what slope is. It's change in y over change in x. It represents how steep this line is and whether or not this line is steep going up or steep going down, going in the opposite direction. Well, in this case, our change in y is change in x dimension, displacement, over change in the x, which will be change in time. Well, that is our equation for velocity in the x direction. So as long as we look at the slope of the line, we can actually tell quite a bit about what's happening with velocity. First thing we can look at is determine what's the direction of the velocity vector. Well, if this slope is positive, velocity has to be positive. All right, so I'm going to put a little plus sign right here. And then all I need to do is calculate the steepness of that slope. And once I calculate the steepness of that slope, I get some number that I'm going to put right here. Okay, and that would be, in essence, the average velocity within that period of time. Okay, well, let's continue. Well, now let's say after this point, and I'm going to again exaggerate a bit here. I'm going to do like this. This is the second phase that we're interested in. Well, again, what do we know about velocity just by looking at the graph? Well, one is that's a positive slope. So we know velocity is going to be positive. The person's moving forwards. What else do we know? Well, we know that is steeper than that one. That's a steeper slope, positive slope than this one. So that means the magnitude of velocity is greater. All right, so I haven't done any math, but I'm looking at the relationships here of what's happening of the horizontal position over time and actually getting information about velocity over time. I know that velocity is positive in both of these regions and that velocity was this much, whatever that number is, and velocity was greater over here. All right, now I'm going to draw a third line here. I'm going to draw like that. Exaggerating a bit here, but that's okay. Well, now what do we know? Well, what's the direction of velocity vector? What's the direction of this slope? That slope is positive, therefore velocity has to also be positive. And how's the steepness of that slope compared to this one? It's less. So the magnitude of velocity is going to be less here than here. Now, I don't know, is that one here? That one, these two are pretty close the way I've drawn them. Maybe this one's a little less steep, so I'll just draw it a little bit lower. So again, now we've got some neat velocity information. I'm at this speed at this moment in time. Now I'm at a faster speed, magnitude of velocity vector, and then I'm at a slower speed. I'm at this velocity, I'm at a greater magnitude of velocity here, running faster, and then I'm still running forward because this is still positive velocity, but now I'm not running as fast as I was in the middle of that run. All right, now I'm going to draw one more line here, right at the turnaround. And for a brief moment in time, there's no change in position. Well, now what does that tell me about velocity? Well, if there's no slope, velocity has to be zero because velocity is equal to, and I'm going to use x here, final position minus initial position divided by the change in time. As long as the position is the same, that numerator is going to be zero, and it doesn't matter what the time period is. So that velocity is zero. Well, if you remember from slopes, that is a zero slope, so velocity has to be zero. Okay? All right, well, good. Now we're getting somewhere in terms of describing what's happening. I start at zero velocity, I go to this velocity, then I go to a faster velocity, then I go to still a forward velocity, but it's not as fast. So what's happening? Well, I'm speeding up and then I'm slowing down. I'm speeding up, I'm slowing down. And of course, that's logical. If you think about a shuttle run, what do? You speed up in the beginning, you hit some peak velocity, and then you have to slow down in order to turn around. And now I'm stopped here for a brief second, and now I'm going to turn around and go backwards. All right, I'm going to draw that backwards. First one like that. Now what direction is that slope? That slope is negative. Therefore, I'm going to put a little minus sign down here. And now I can calculate the steepness of that slope by calculating our xf minus xi divided by the change in time. And I'm just going to put a number down here, or some value representing that dot right there. Now I'm going to run faster, so I'm going to have a steeper downward slope. Oops. What direction is that slope? It's negative. The steepness of that is greater than the steepness of that, so I'm going to have a greater negative velocity. And then at the end, I'm going to slow down, negative slope, less negative velocity, and the steepness of the slope is less than this one, maybe comparable to that one, maybe a little bit less. Wow, okay, so I haven't done any math, but now I can understand velocity. And I'll go ahead and connect these dots just for the sake of discussion, just so you can see a pattern of velocity that's happening here. Well, I'm speeding up. I reach some peak velocity about midway through the run to the cone. Then I'm slowing down. I stop for a brief moment, and then I start running back towards the origin. I hit the fastest velocity going backwards, and then I slow down, ultimately stopping at the finish line. If you stop, a lot of times people run through it, but we'll do stop. So if we look at our picture, we start off at this position, we run, and we get faster and faster and faster, and then we slow down, slow down, slow down, stop. Then we run backwards, faster, faster, fastest. Then we start to slow down, slow down, slow down, and then stop. And that's exactly what this plot tells us. Speed up, slow down, speed up, slow down. Forward direction, because the velocities are forward. Forward direction, because our velocities are all forward. Backward direction, backward direction. All right. So we can now write down a few things. I'm going to abbreviate. I'm going to say speeding up, moving forward in this region right here. Okay. Over here, I'm going to slow down, still moving forward up until we cross that zero. Then in this phase, we're going to speed up, moving backwards. And then we're going to slow down, moving backwards. And then we're stopped. All right, so we have a nice kinematic description of the shuttle run in terms of what's happening with velocity. Well, now let's look at the acceleration during the shuttle run. Well, remember the slope of the velocity versus time plot is now going to be delta V over delta T, changing whatever's on the y-axis, which is now velocity, over change on whatever's on the x-axis, which is now time, and that is our formula for acceleration. So when we look at the slope of the velocity versus time plot, that tells us everything we need to know about acceleration. So let's do this. I'm going to drop these dashed lines down here, just so we can see it and see that these all have to line up in time. So it's good to draw these plots right on top of each other. So now what I want to do is a good exercise is to identify at least the direction of the acceleration vector. All right. We can deal with the magnitude of acceleration later. But at this point, if we can sit back and we can identify the direction of the velocity vector for each of these regions, we can claim victory. Well, let's do that. Well, what direction are these slopes anywhere in this region? Anywhere in this region, the slopes are positive. Well, acceleration has to be positive. Why? Because A equals VF minus VI over TF minus TI. If velocity is 2 meters per second, final, over zero, maybe starting at 0 meters per second, 2 minus 0 divided by any period of time is going to be a positive number for acceleration. All right, so anywhere in this region, the direction of the acceleration vector is positive, and that means speeding up, going forward. What direction are the slopes in this region? These are all negative slopes, so acceleration has to be negative. If I'm at 2 meters per second here, and this is 4 meters per second, this is final, this is initial, so 2 minus 4 is going to be a negative 2 meters per second divided by any time period. That's going to be a negative acceleration. So anywhere in this region, anywhere where the slope is negative, acceleration is going to be negative. The direction of the acceleration is going to be negative. And in this kinematic analysis, this means slowing down, moving forward. So slowing down, moving forward. All right, let's look at it a little further. What direction are these accelerations? These are all, what direction are all these slopes? These slopes are all negative. Acceleration has to be negative. If my final velocity is negative 4 meters per second, and my initial velocity is 0 meters per second, negative 4 minus 0 is a -4 divided by any time period. Acceleration is going to be negative. The direction of the acceleration will be negative. Well, look at this. This is speeding up, but moving in the backward direction. This negative acceleration was slowing down, moving forward. The direction of the acceleration vector does not tell us the direction of movement. What it tells us is the direction of the slope of the velocity versus time plot. All right, one final region here. What direction are these slopes? They're positive, so acceleration has to be positive. The direction of the acceleration has to be positive. Final velocity 0, -4, because we're in the negative region here of velocity, -4, initial, so 0 minus -4 is +4. So acceleration has to be positive. So the math all holds up, as does the graphical representation. Key points. The slope of the position versus time plot tells us everything we need to know about velocity. So the slope of the position versus time plot tells us everything we need to know about velocity. And what is that? Everything? It's magnitude and direction. Okay. The other important point is the slope of the velocity versus time tells us everything we need to know. We need to know about acceleration. Oh, I should put V. Need to know about V. And what is that? Everything? It's magnitude and direction. The final real take-home point from this final point is that the direction of the acceleration vector does not tell us direction of motion, does not tell us direction of motion. Really important, okay? Really, really important. And why is it important? Because we are going to take our understanding of acceleration and we're eventually put it in this equation, which I'm sure you've heard, F equals ma. And if we can get a great understanding of acceleration, then we can really understand the forces that are going to cause that acceleration. So that's why it's really important to get this understanding of the acceleration vector. All right, I want to do one more thing in this presentation and just give sort of a little bit of a sidebar in terms of slopes, because you want to get comfortable with understanding slopes. So let me do a bigger plot here. And I'll just put a Y here and I'll put an X here, because this could be position versus time, this could be velocity versus time, what have you. All right, now if I have some slope here, we know that that's going to be positive. If I have another slope like that, that's going to be more positive. And if I have another slope like that, that's even going to be more positive. All right, now this slope would be 0, and I'm going to draw, this is going to be a negative slope, this is going to be more negative, and this would be even more negative. And I kept all those in that one region up here. But realize if I redraw any of these slopes down here, that is also the same slope here. That's still a positive slope, a positive slope, a 0 slope, negative, more negative, and more negative. But the interpretation of what's going on up here versus what's going on down here may be quite different because we're in these different regions. So for example, if I did this plot again as velocity versus time, and I have that slope, I have that speeding up, moving in the forward direction. Whereas this slope, the same slope, would be slowing down, moving in a backward direction. All right, so where these slopes fall on the velocity plot really changes our understanding or our description of kinematics. But you should be able to identify graphically how these slopes relate to each other, and that will ultimately help us in understanding these relationships between position, velocity, and acceleration. Okay, I think that's it for this one. Thank you.